Welcome to Cloud Deck's video lessons. Okay, let's dive right into this comprehensive explainer designed specifically for your DGCA CPL exams. Today, we're going to decode the macro to micro technologies that track our every single move in the sky. We are literally tearing down the invisible web of flight, from satellites orbiting the Earth all the way down to the mechanical heartbeats of your flight instruments. We'll be following a strict exam blueprint structure today. So we're starting out in space with the Global Navigation Satellite System, moving down through the atmosphere with radar, and finishing up right inside your glass cockpit with inertial navigation. Let's get right into it. Section 1. GNSS Architecture and Geometry. Let's start with the big picture and look at how your aircraft actually calculates its exact position from space. The GPS system operates through three distinct but completely interdependent segments working together. Think of it like a giant dynamic puzzle. First, we have the space segment, which is an active constellation of 31 operational satellites flying in medium Earth orbit. That's an altitude of roughly 20,200 kilometers. Next up is the control segment. This is the ground-based monitoring handled by Space Force and Air Force personnel, known as Team Blackjack, operating out of Colorado, who constantly tracks satellite health and orbits. And finally, the user segment. That's your aircraft's receiver equipment, like the Garmin G1000, pulling in and processing those signals. Now, to find your position, the receiver has to figure out its exact distance to each satellite. It does this by measuring what we call a pseudo-range. Basically, it takes the time the signal traveled and multiplies it by the speed of light. But here's the catch, and this is why it's a pseudo-range and not a true range. Because your Garmin doesn't have a multi-million-dollar atomic clock inside it like the satellites do, its internal crystal clock isn't perfectly synchronized. So this measurement inherently includes a time bias error. Which brings us to the absolute golden rule of GPS for your exams. Because you have to solve for 4 specific variables of three-dimensional space and time, that's your latitude, longitude, altitude, and that receiver clock bias we just talked about, your receiver absolutely must lock on to a minimum of 4 satellites simultaneously. Write that down because it's absolutely crucial. Now, looking at the geometry of these constellations, we run into something called geometric dilution of precision, or GDOP. You see, just having 4 satellites isn't quite enough if they're in the wrong spots. Even with 4 solid signals, if those satellites are clustered tightly together in one tiny corner of the sky, your position accuracy degrades rapidly because the angles of intersection are just too shallow. The mathematically optimal configuration, which gives you a low or excellent GDOP, is having 1 satellite directly overhead and 3 others spaced equally 100 degrees apart, low on the horizon. Moving on to Section 2, GPS errors and RAIM. Now that we know how it works in a perfect world, what happens when signals get distorted? Let's look at how this builds your exam knowledge on error sources. Ionospheric delay is by far the largest source of natural error. It actually stretches and slows signals by up to 15 meters as they pass through solar-charged atmospheric gases. Lower down, tropospheric delay adds some minor errors from weather variables. Meanwhile, multipath errors happen locally when signals literally bounce off nearby terrain, buildings, or even your own aircraft's fuselage before hitting the antenna, which totally confuses the receiver. Because of all these errors, to ensure our safety during instrument flight rules, we use Receiver Autonomous Integrity Monitoring, better known as RAIM. This is essentially your GPS independently verifying its own accuracy. Memorizing these specific satellite counts is vital for your exams. You need 5 visible satellites for simple fault detection. But to actually identify which satellite is lying to you and exclude it, that's fault detection and exclusion, or FDE, you need 6. And keep in mind, if you input your current altimeter setting, known as baroating, the receiver uses your altitude as a virtual satellite. That smartly reduces your requirement by 1. The takeaway here, never trust GPS blindly. If RAIM detects a fault and cannot exclude it, or if you simply don't have enough satellites in view, your GPS is going to flag an integrity fault. Standard procedure dictates that you do not use that GPS data for primary navigation. You must immediately transition to alternative navigation sources like your VORs. All right, Section 3, primary versus secondary radar. We're leaving space and entering the atmosphere where air traffic control uses completely different tech to track you. You might be wondering, why doesn't ATC just use one single type of radar to manage the airspace? Well, it really comes down to the fundamental physics of how radio waves reflect off surfaces versus how they can be actively transmitted. This comparison brilliantly illustrates the difference. Primary surveillance radar, or PSR, is essentially just a passive echo. It blasts a high-frequency pulse that bounces off your metal airframe and travels all the way back to the dish. Because the signal travels both ways, it suffers from the inverse fourth power law, meaning it loses its energy extremely fast and requires massive amounts of power. Plus, it can't tell ATC who you are or what your altitude is, and it gets easily blocked by heavy weather. Secondary surveillance radar, on the other hand, is an active conversation. The ground station interrogates your aircraft on 1030 MHz, and your transponder replies with a fresh, strong signal on 1090 MHz. This relies on an inverse square law, requires way less power, and completely bypasses weather clutter because of those separated frequencies. Section 4. Transponder modes. So when that secondary radar signal hits your aircraft, what exactly does your transponder say back? Let's look at the older, traditional transponder formats first. They're pretty straightforward. Mode A provides identity tracking only. It just gives ATC your 4-digit octal squawk code, which is severely limited to just 4,096 possible combinations. Mode C takes that up a notch. It pulls data from an encoding altimeter, automatically transmitting your pressure altitude in 100-foot increments alongside that identity code. But as the skies got busier, those 4096 codes just weren't enough. Mode S is the modern standard, and it's a real game changer. It solves that code starvation issue by assigning a permanent, unique 24-bit address for your aircraft, giving us over 16 million possible codes. It also refines altitude reporting down to much tighter 25-foot increments. Because ground sensors can selectively interrogate your specific 24-bit address, Mode S eliminates overlapping transponder replies, which is often called garbling or fruit. Ultimately, Mode S acts as the essential backbone for your traffic collision avoidance systems, or TCAS, and your ADS-B data links. Bringing us to Section 5, Gyroscopes and Inertial Navigation. What happens when external signals completely fail? Well, your aircraft relies entirely on internal physics. And to truly understand mechanical flight instruments like the turn coordinator or the attitude indicator, you absolutely must master the concept of gyroscopic precession. It's a bit counterintuitive, but if you apply a physical force or torque to a spinning gyro, that force doesn't push the gyro exactly where you pressed it. Instead, the resulting reaction force manifests exactly 90 degrees further along the direction of rotation. This predictable physics quirk is exactly how older mechanical instruments turn physical motion into the dial readings you see in the cockpit. Now let's look at inertial navigation systems, or INS. These systems figure out where you are without looking outside at all. They use accelerometers to measure specific force, which is physical acceleration due to vehicle motion. But the sensor also feels Earth's gravity, right? So the navigation computer mathematically subtracts the gravity vector to isolate your true kinematic acceleration. Then it uses calculus, specifically double integrating the acceleration data to calculate your exact velocity and plot your exact position. It's brilliant! Of course, traditional spinning metal gyroscopes suffer from friction and cumulative drift over long flights. Modern aircraft solve this by using ring laser gyros in strap-down configurations. They completely eliminate moving mechanical gimbals by using counter-rotating light waves to measure rotational changes. But here is a hot tip for your exams. Keep an eye out for questions about the dither motor. You see, at very low rotation rates, the frequencies of these two lasers can actually bleed together in a phenomenon called laser lock. The dither motor simply vibrates the entire unit rapidly to prevent those light waves from locking together. So as we wrap up this explainer on the critical systems that guide aviation today, consider this. With advanced RAIM algorithms improving our satellite integrity and emerging quantum gyroscopes promising to reduce INS drift by a factor of 100 on the horizon, the invisible web of flight is only going to get tighter, safer, and infinitely more precise. Are we approaching an era where an aircraft will never truly need to look outside to know exactly where it is? We're going to dive into pitot-static systems, airspeeds, and magnetic compasses in part 2 of this series, but for now, that is definitely something to think about as you study. Good luck with your